For 10,000 years, a silent, steadfast partner has fueled our ascent. It is not a metal, nor an invention of our own design. It is the soil. From the Fertile Crescent to the terraced hillsides of the Andes, this living, breathing skin of our planet has been the foundation of civilization. Every city, every empire, every great leap forward for humanity has been built upon its promise that a seed planted will become food, that a harvest will sustain a people, that a future is possible. We learn to read its moods, to follow its seasons, to harness its incredible power. This intimate relationship with the land defined us. It was the bedrock of our economies, the heart of our cultures, and the source of our security. But in the last century, something profound shifted in that relationship. We demanded more. The Green Revolution of the mid-20th century was a marvel of human ingenuity. With high-yield crop varieties, synthetic fertilizers, and chemical pesticides, we achieved yields that were once unimaginable. We fed billions and staved off the famines predicted by many. It was a victory, but a costly one. This triumph gave us abundance, but it also sowed the seeds of dependence and degradation. We began treating soil not as a living ecosystem, but as an inert medium, a mere substrate to be pumped full of chemicals. This industrial model, for all its productivity, has pushed our foundational resource to a breaking point. Now that foundation is cracking. The United Nations reports that a third of the world's soil is already moderately to highly degraded. We are losing fertile land at a staggering rate. An area the size of Costa Rica vanishes every single year due to erosion, desertification, and pollution. This isn't a distant, abstract problem. It's a crisis unfolding under our feet. The very ground that has sustained us for millennia is becoming exhausted, saline, and stripped of the organic matter that gives it life. The causes are a complex web of our own making. Intensive tillage that exposes topsoil to wind and rain, overgrazing that leaves land bare, and the relentless application of chemicals that disrupt the delicate microbial communities essential for soil health. Compounding this is the ever-growing demand from a global population set to approach 10 billion people by 2050. More mouths to feed from less and less productive land. This is the paradox of our time. To truly understand what we're losing, we must look closer. A single handful of healthy soil contains more living organisms than there are people on Earth. It is a bustling, subterranean metropolis of bacteria, fungi, protozoa, and nematodes. This microscopic world is the engine of life. Fungi form vast networks, transporting water and nutrients to plant roots in exchange for sugars. Bacteria fix nitrogen from the atmosphere, providing a natural fertilizer. Earthworms and other invertebrates act as tireless engineers, aerating the soil and composting organic matter. This intricate dance of life is what creates fertility. It's what holds water, prevents erosion, and even regulates our climate by sequestering vast amounts of carbon, more than all the world's forests and atmosphere combined. When we degrade our soil, we are not just losing dirt. We are silencing an ancient, life-giving ecosystem. We are breaking a fundamental link in the chain of life. The stakes could not be higher. Food security, clean water, and a stable climate all depend on the health of this fragile layer. But humanity has always been defined by its response to crisis. Faced with this monumental challenge, a new generation of farmers, scientists, and engineers is asking a radical question. What if we could grow food without soil at all? What if we could create perfect growing conditions anywhere in the world, independent of climate or geography? The next agricultural revolution is dawning, and it looks nothing like the last one. It's a revolution that is moving indoors, into climate-controlled environments where every drop of water and every photon of light is precisely managed. It's a revolution that is moving upward, stacking farms into vertical towers in the heart of our cities, slashing food miles and bringing unprecedented freshness to urban populations. And, in some cases, it's even moving underwater, cultivating new sources of protein in contained, sustainable systems. This is the world of Controlled Environment Agriculture, or CEA. It's a suite of technologies that allows us to decouple food production from the land. Within these high-tech farms, we can create bespoke recipes of light, nutrients, and temperature, tailored to the exact needs of each plant. This precision allows for staggering yields, year-round production, and a dramatic reduction in resource use. We can grow more with up to 95% less water than conventional farming, and with no need for chemical pesticides, herbicides, or fungicides. This isn't science fiction. It's happening right now in warehouses, shipping containers, and purpose-built facilities around the globe. It represents a fundamental rethinking of how we produce the most essential human need. It's a shift from exploiting nature to collaborating with it, using technology to replicate its best attributes in a controlled, predictable, and sustainable way. This journey will take us from the crisis in our fields to the cutting edge of innovation, exploring the technologies and the pioneers who are building the farms of the future. The challenge is immense, but the promise is nothing short of revolutionary. A food system that can nourish our growing population while helping to heal our planet. The next harvest is being planted. Welcome to CEA. Every crop follows a digital recipe. No soil, minimal water, zero pests. Food is grown close to cities, slashing transport emissions. The hurdle? Energy. But CEA is evolving alongside clean energy tech. For millennia, farming has been an art of intuition, a deep, personal connection between the farmer and the land. It was a practice of walking the rows, feeling the soil, and reading the subtle language of the leaves. But as our global population swells and our arable land shrinks, this traditional approach, while noble, is reaching its limits. The challenge is no longer just about growing food. It's about growing more, with less. Less water, less land, and a dramatically smaller environmental footprint. This is the dawn of a new agricultural revolution, one driven not by the plow, but by data. Welcome to the world of precision agriculture. At its core, precision agriculture is a management philosophy that uses information technology to observe, measure, and respond to variability within and between fields. Instead of treating a 100-acre field as a single, uniform unit, it sees it as a complex mosaic of thousands of unique microenvironments. Each square meter has its own specific needs for water, nutrients, and pest control. The goal is to provide exactly what is needed, precisely where it is needed, and only when it is needed. This hyper-targeted approach is made possible by a symphony of advanced technologies, creating a digital nervous system for the farm. The most visible pioneers of this new era are unmanned aerial vehicles, or drones. These are the farm's new eyes in the sky, capable of seeing what the human eye cannot. Equipped with sophisticated multispectral or hyperspectral cameras, they capture data from across the light spectrum, far beyond our limited visible range. Healthy plants, rich in chlorophyll, absorb red and blue light for photosynthesis, but strongly reflect near-infrared light. Stressed plants do the opposite. By analyzing these unique spectral signatures, we can generate detailed health reports for the entire field. The most common of these is the Normalized Difference Vegetation Index, or NDVI. It's a simple yet powerful calculation that transforms raw sensor data into an intuitive color-coded map. Lush, healthy vegetation appears as vibrant green, while areas of stress, caused by drought, nutrient deficiency, or disease, show up in shades of yellow and red. This allows a farmer to spot a problem from 400 feet in the air, days or even weeks before it would be visible to someone walking the ground. While drones provide on-demand, high-resolution snapshots, they are complemented by their counterparts in orbit, satellites. For decades, programs like the U.S. Geological Survey's Landsat have provided invaluable, large-scale data to scientists and governments. Today, a growing constellation of commercial satellites offers more frequent and higher-resolution imagery to the agricultural sector. Satellites excel at monitoring regional trends, tracking crop development over Zhengzhou seasons, and providing a baseline of health for vast areas. A farmer might use satellite data to monitor overall growth patterns across their entire operation, then deploy a drone to investigate a specific area of concern flagged by the satellite imagery. They are not competing technologies, but rather a collaborative system of observation, offering both the panoramic view and the microscopic detail. But collecting this data is only half the battle. The sheer volume of information from a single drone flight can be overwhelming. This is where artificial intelligence becomes the farmer's indispensable partner. AI-powered analytics platforms act as the brain of the operation, ingesting terabytes of data from drones, satellites, ground sensors, and weather stations. Machine learning algorithms, trained on millions of images of healthy and diseased crops, can automatically identify and classify issues with incredible accuracy. They can distinguish between nitrogen deficiency and a fungal infection, or between water stress and pest damage. More than just a diagnostic tool, the AI moves into a prescriptive role. It synthesizes all the incoming data and generates precise prescription maps. These are detailed GPS-coded instructions for field machinery, dictating the exact amount of fertilizer, pesticide, or water to be applied to each specific zone of the field. The farmer is no longer guessing. They are acting on a data-driven, scientifically backed recommendation. This brings us to the final step: targeted intervention. The prescription map is loaded into the onboard computer of a GPS-guided, variable rate tractor. As the machine moves through the field, it automatically adjusts the application rate in real time, delivering more nutrients to a deficient patch and none at all to a healthy one. The savings are immense. Farmers report reductions in fertilizer use by up to 30% and herbicide use by as much as 90%. This isn't just an economic victory, it's a profound environmental one. Less chemical runoff into waterways, less nitrous oxide released into the atmosphere, and a significant reduction in water usage. For smaller, more targeted tasks, the drone itself completes the cycle. What was once the scout now becomes the sprayer. A small, agile drone can be dispatched to a precise GPS coordinate to spot spray a nascent weed patch or a localized pest outbreak using a fraction of the chemicals a traditional broadcast sprayer would. The drone is now the scout, the scientist, and the surgeon, performing precision strikes to protect the health of the whole. Consider the case of Cedar Creek Farms in Iowa. For generations, they battled a persistent issue with iron chlorosis in their soybean fields, a nutrient deficiency that turns the leaves yellow and stunts growth. Traditionally, they applied expensive iron chelate fertilizer across entire fields, a costly and inefficient solution. By adopting precision agriculture, they began flying a multispectral drone weekly. The resulting NDVI maps clearly delineated the exact boundaries of the chlorosis-affected zones, which shifted slightly each year depending on soil moisture. The AI platform analyzed this data and generated a variable rate prescription. Now, their applicator only sprays the iron treatment on the 15 to 20% of the field that actually needs it. The result? A 75% reduction in their iron fertilizer costs, and more importantly, a 10 or 15% increase in yield from those previously underperforming areas. The technology paid for itself in a single season. This isn't a futuristic fantasy. It is the reality on the ground and in the air for a growing number of farms today, transforming the economic and ecological calculus of modern agriculture. Our oceans, the cradle of life, are sounding an alarm. For millennia, they have been a seemingly inexhaustible source of sustenance, but today they are under unprecedented strain. Decades of industrial-scale overfishing have depleted wild stocks, pushing many species towards the brink of commercial, and in some cases, biological extinction. The United Nations Food and Agriculture Organization reports that over a third of global fish stocks are now fished at biologically unsustainable levels. Beyond extraction, our marine ecosystems are choking on pollution, from plastic debris to agricultural runoff that creates vast, oxygen-deprived dead zones. Traditional aquaculture, while developed to relieve pressure on wild fisheries, has often brought its own set of environmental challenges. Open net pens, the dominant form of fish farming, can release waste, uneaten feed, and pathogens directly into the surrounding waters, impacting local ecosystems and wild populations. The very system designed to supplement our seafood supply is now contributing to the stress on our marine environments. It is a paradox that demands a radical rethinking of how we produce one of the world's most critical sources of protein. We stand at a crossroads, needing a solution that can provide for a growing global population without further mortgaging the health of our planet's blue heart. The answer, for a growing number of innovators and nations, is not to look further out to sea, but to look inland. This is the dawn of the blue revolution on land, powered by a technology known as recirculating aquaculture systems, or RS. Imagine a pristine marine environment, perfectly balanced and self-sustaining, but instead of being in the ocean, it's housed within a facility hundreds of miles from any coastline. This is the core principle of RS. It is a method of land-based fish farming that replicates the delicate biological and chemical balance of the sea in a completely controlled, closed-loop environment. By continuously recycling and treating the water within the system, RAS facilities can raise fish at high densities with astonishingly minimal water usage, often using less than 1% of the water required by traditional pond or raceway aquaculture systems. This is not just farming, it is aquatic life support on an industrial scale, a technological ecosystem designed for optimal fish health and sustainable production. It represents a fundamental shift from harvesting a resource to cultivating it with precision, care, and a profound respect for the natural world it emulates. The heart of any RAS facility is its sophisticated, multi-stage water treatment process. It's a complex dance of physics, chemistry, and biology, engineered to perfection. The journey begins as water leaves the fish tanks, carrying waste products, primarily solid feces and dissolved ammonia excreted by the fish. First, it enters the mechanical filtration stage. Here, large rotating drum filters, lined with fine mesh screens, physically capture and remove the solid waste before it can break down and foul the water. This waste, rich in nutrients, doesn't go to a landfill. It can be processed into valuable fertilizer for agriculture, creating a circular economy. Once the solids are removed, the water flows to the most critical component, the biological filter, or biofilter. This is where the magic of nature is harnessed. The biofilter is a habitat for vast colonies of beneficial bacteria. In a two-step process called nitrification, one group of bacteria consumes the toxic ammonia, converting it into a less harmful compound called nitrite. Then, a second group of bacteria consumes the nitrite, converting it into nitrate, a compound that is relatively harmless to fish, even at higher concentrations. This biological engine is the system's liver, constantly detoxifying the water and making it safe for recirculation. But the purification doesn't stop there. To ensure the highest level of biosecurity and water quality, the filtered water undergoes sterilization. High-intensity ultraviolet, or UV, sterilizers act as a gatekeeper, using light to destroy the DNA of any free-floating bacteria, viruses, or parasites, preventing the outbreak and spread of disease. Some advanced systems also employ ozone injection, a powerful oxidizing agent that breaks down residual organic compounds and further disinfects the water, leaving it crystal clear. Finally, before the water returns to the fish, it is reoxygenated. Pure oxygen is dissolved into the water at precise levels, creating a perfect, oxygen-rich environment that minimizes stress and promotes vigorous growth, far more stable than the fluctuating oxygen levels found in the wild. This entire loop, from tank to treatment and back again, is governed by a network of sensors monitoring every vital parameter in real time: temperature, pH, salinity, dissolved oxygen, and nitrogen compounds. This data feeds into a central control system, allowing operators to maintain the perfect aquatic habitat 24 hours a day, 7 days a week. It is a proactive, not reactive approach to animal husbandry. This level of control allows RAS to be tailored to the precise biological needs of specific species. For Atlantic salmon, the system can mimic the cold, pristine waters of a Norwegian fjord. For barramundi, it can replicate a warm, tropical estuary. By eliminating environmental stressors and the threat of predators and disease, fish grow faster, healthier, and more efficiently. Feed conversion ratios, or the amount of feed required to produce 1 kilogram of fish, are significantly better in RAS than in many traditional systems. This precision also provides unparalleled biosecurity. Because the system is enclosed and isolated from the outside world, the risk of introducing diseases is virtually eliminated. This means fish can be raised without the need for antibiotics or vaccines, a major advantage for consumer health and a stark contrast to the challenges faced by open water farms. This biosecure, controlled environment is enabling a new geography of food production. Countries with arid climates and limited coastlines, like Saudi Arabia, are investing billions in RAS to achieve protein independence and food security in the face of climate change. They are building massive inland salmon farms in the desert, a feat unimaginable just a decade ago. Meanwhile, established seafood powerhouses like Norway are embracing RAS not to replace their iconic fjord farming, but to complement it. They use land-based systems to grow juvenile salmon, called smolts, to a larger, more robust size before transferring them to sea pens. This shortens the time fish spend in the ocean, reducing their exposure to sea lice and other environmental risks, thereby improving overall sustainability. As a case study in this global movement, consider Atlantic Sapphire's facility in Miami, Florida. Dubbed the Blue House, it stands as one of the largest land-based salmon farms in the world. Its location was chosen strategically, placing a massive protein production center right at the doorstep of the vast American market. This drastically cuts down on food miles. Instead of flying salmon fresh from Norway or Chile, which carries a significant carbon footprint, the Blue House can deliver its product to retailers and restaurants across the eastern seaboard within 24 to 48 hours of harvest. This ensures a fresher product for consumers and a more resilient supply chain, insulated from the disruptions of international logistics. The facility operates on a massive scale, with a mission to produce tens of thousands of metric tons of salmon annually. It demonstrates both the immense promise and the formidable challenges of RAS. The project has faced technical and biological hurdles, highlighting the operational complexity and steep learning curve involved. Yet, its continued operation and expansion serve as a powerful proof of concept, paving the way for a future where fresh, sustainable seafood can be produced almost anywhere on Earth, bringing the ocean's bounty inland and securing a vital food source for generations to come. These aren't siloed technologies, they're a system. Vertical farms for greens, precision ag for staple crops, RAS for protein. Together, they form a decentralized, sustainable food future. Soil and water once grew our food. Now it's data, design, and closed-loop systems. Innovation is the new soil. What do you think is the biggest hurdle? Comment below. Like and subscribe for more from Eco Innovatech.